Hey guys, it's just me, Mr. Wee. Just continue on with what is it? With L'Hopital's rule. So the next part's going to be called indeterminate products. So this is possibly so go ahead and write these notes down for yourself. Okay. Um, this is just a scenario where you have, if you're taking a limit, and let's say you have it in such a way where the function that you're taking the limit to, like x equals, or x approaches 0 from both sides of x times 4 over x, leads you to an indeterminate product. So if you remember back to one of the forms of indeterminate numbers that we cannot have as a solution for a limit is 0 over 0, infinity over infinity, and 0 times infinity, and or infinity times 0, some kind of indeterminate product. Or that'll kind of give you a clue. The next part we're probably going to look at infinite, or like we're going to have the difference between indeterminate forms, but right now we're looking at indeterminate products. Okay, so sorry about this. Go ahead and you can pause this for a second, or you can let me kind of talk as you write this down. Okay, so in this case here, if I have the limit as x approaches 0, as you have a function that is x times 4 over x, it would be like having 0 times 4 divided by 0, which would be 0 times infinity. But in this case here, this is an easy solution. For this, you don't have to do anything abnormal. You would just simply cross out the x and the x over here, and then you get a limit of 4. So the x times 4 over x, interestingly enough, by itself, if you just left it in its pure raw form, that should tell you that there's no solution. This function does not have a point at x equals 0. But if you're looking for just the limit, we can have x times 4 over x, and the x's would cancel out, giving you a limit of 4. So the function approaches 4, but there's no actual value of 4 there. So if you look on Desmos, or you graph this out, you're going to find a nice function that looks continuous, but if you look very closely at x equals 0, there's no point, because it's indeterminate. So it won't actually get, it'll be like a hole, but it's approaching a y value of 4. Okay, but just letting you know, you're not going to get something that convenient. I'm just letting you kind of see that this is a form of an indeterminate product, okay, where you have 0 times infinity if you do substitution of the number that x is approaching into the function. Okay, here's another example. This is something that you cannot simply just simplify down and cross off x's, because they're in the numerator and denominator. You have x squared times the cosecant of x. So in here, if you plugged in 0, I'm sorry, let me kind of get rid of this here. If you have x approaches 0 from the negative side, and you plug this in, it'd be like a bunch of negative numbers plug into x squared. Essentially, you'd still get 0 because they're approaching 0. Okay, or it'd just be, if you just plug in 0, it'd just be 0 squared. It'd be 0 times, and remember, if you're going to take the cosecant of x, you're approaching 0 from the negative side, so it's a bunch of little small negative numbers approaching 0. So you get negative infinity. But again, in either case, 0 times infinity, if that makes sense to you, or more technically correct, it's 0 times negative infinity, you won't get a proper limit. You get this indeterminate form. And then over here, it's the same thing. So you have x times the sine of 1 over x. I mean, I have the limit values here and here, but just letting you know before we get to those solutions, you're going to get this weird indeterminate form. So, I mean, it should be the limit is equal to 0 and the limit of this statement is equal to 1. But initially, if you just plug in substitution, you're not going to get those answers. There's a different solution for how to get these answers. Okay, so what you're going to do is you essentially want to rewrite what you have. Like in this case, I have, like, if you look at it, you can look at x as like its own separate function, and 4 over x as a separate function. So we'll call this like f and g. If you look at it, if you look at all these statements here, typically what gives you indeterminate products is if your function is written as in a way that looks like it's two different functions being multiplied to each other. f times g. So all of these kind of look like f times g. X squared would be f, your cosecant x would be g, and in this case, maybe a function g or f could be x, and the other one would be sine of 1 over x. Okay, the whole point is, though, in order to solve these, is you're going to have to rewrite this in a way where it's not necessarily different from this, but it looks different, such as this. What if you rewrote this as f divided by the reciprocal 1 over g? That is the same thing as saying f times g, just seemingly in a more convoluted way or more complicated way. F divided by 1 over g is the same thing. It's equivalent to f times g. It just looks very different. Or you can write it as this. You can keep g, and then you can change f as 1 over f, but you'd have to divide it. So you'd have g over 1 over f. And this is, again, to apply L'Hopital's rule, because at this point, what you can do is you can apply the derivative. You can find the derivative of the top guy here and the derivative of the bottom guy here, and then cancel stuff out until where you can plug in your x approaches value, or your value that x is approaching for the limit. Okay, so that's a lot of talk. Hopefully you have this written down. Now, let me give you some examples. Okay, so here's an example of indeterminate products and what you would have to do with indeterminate products using this sort of newer rule. I mean, it's the same kind of rule. It's the same L'Hopital's rule, but you're just rewriting things to make it look in a way where you can apply L'Hopital's rule. So here's an example of things that give you indeterminate products. So this would give you an indeterminate product here. So technically speaking, I know that this one you can just cross out the x's, but let's just apply this new technique I just showed you to this example so I can easily show you what you're supposed to do. Okay, so again, don't cross out the x's. You can, okay, but I'm just saying this is just for the purposes of showing you this example. What I can also do is, right now I have the limit as x approaches 0, sort of like in the way that it's f times g. X is f and then g is 4 over x. But remember, the whole point is to rewrite this as limit as x approaches 0 of f, maybe f divided by 1 over g. And what would that look like? It would be x as x approaches 0. I could rewrite this as x divided by x over 4. I remember, and I would just take the reciprocal of g. 1 over g would basically, what that means is you take g and then you flip it. You flip the numerator down the denominator, and now the denominator becomes the numerator, but you have to divide that value because this is still equal to this mathematically and algebraically. I don't want to skip any steps, so to make sense of this, and I mean, some of you guys might already notice that the x's will cancel out. If you forget why algebraically, or you don't know why, because I've always done this when I was a kid, and I just realized as a teacher through more years of experience that it's not quite intuitive for you guys to cancel this out. If it just doesn't make sense to you, you can rewrite the top portion as x over 1, because x is essentially just x divided by the number 1, not 0. Okay, remember, anything divided by 0 is eventually infinity, so that's not true. So it's divided by 1, divided by x over 4, and then what happens is the numerators can cancel out, giving you 1 and 1 here, and you're going to get the limit of essentially x approaches 0 of 1 over 1, which is just 1. Okay, 1 divided by 1, which is just, this would just be 1. You're going to have 1 divided by 4, and then you have the limit as x approaches 0 of 1 divided by 1 over 4. Okay, and I can't even substitute 0 in, but this will give me a value, okay, a constant value, which totally works for a limit, right? So we 1 divided by 1 over 4, which would just give me 4, as we originally anticipated. Again, this was just to show you the technique with this function, but I know in this scenario, all you could have done is just cross out the x's, okay? But now let's go back to one of the previous examples, like this one right here. Limit as x approaches 0 from the negative side of cosecant, or x squared times cosecant x equals 0. Sorry about that, I was just scratching my face. And now let's apply that same technique that we applied here to a more complicated problem. Okay, so I'm going to give you one more example, and then, you know what, let's not do more in-class problems, but you may do this at home. I'll give you the last one as like a little thing that you can do on your own to figure this out, and then I'll just show you the solution at the very end. But let's go over this one here, where x approaches 0 from the negative side of x squared times cosecant x. Okay, and just as a reminder, we're going to use this. So if you ever see like cosecants, cotangents, or what was the other one? What am I forgetting? Cosine. Then rewrite it using a trigonometric identity you know about cosecant x. It's the same thing as saying 1 over sine of x. Okay? So what you're going to end up having is this. You're going to have the limit. Remember, you want to identify your f and g. So maybe this I can use as my f, x squared. And then g, I'm not going to use cosecant x. I rewrote it as 1 over sine x. This is going to be my g. Okay? And if I rewrite that now, it'll be x. As x approaches 0 from the negative side, you're taking the limit of f times 1 over g. Okay? Or you can do it the other way around, whatever works for you. Okay? It could be g times 1 over f. And then what that's going to look like now is you're taking the limit as x approaches 0 from the negative side of x squared. I'm sorry, it's such a dope. It's f times, or f over 1 over g. I'm so sorry to confuse you. That's f divided by 1 over g. So it'll be x squared divided by, so remember it's 1 over g, so this is g, so 1 over g would be flipping that. You'd be flipping this into, let's see, it would be sine over x divided by 1. Oh, that's starting to look pretty familiar. And if I rewrite that, that'll be simply x squared divided by sine of x. And at this point, can you plug in 0 right here? Like 0 squared divided by sine of 0. That'd be, wait a minute, 0 squared divided by, if you remember, sine of 0 is still 0. So that's not determinate. That's not a tangible value yet. So that means we apply L'Hopital's rule. Okay, which gives you the limit as x approaches 0 from the negative side, and then now we're going to take the derivative x squared and the derivative sine of x, which is 2x over cosine of x. And now let's see if we can do the substitution of 0. So remember, I just took the derivative x squared and sine of x, so that would be 2 times 0, which is 0. Cosine of 0 is actually 1, and that is a number that checks out, by the way, because 0 divided by any number is just 0. That is not indeterminate. Okay, so that is your final answer. Okay, which is kind of what we talked about up here. Now, why don't you try this one? You can pause it, or actually, you know what? If you're in class, don't pause it to do this. Move on to the next section. But if you need to take a second to write down the solutions, here are the solutions for what you should be doing. Sorry, it's in green, so you can go ahead and pause that right now. I know it's kind of hard to see, but you can pause that right there and then kind of work this out on your own. Okay? So pause that or do whatever you can, because after this is the end of this part, and then we're going to move on to, so sneak peek for part 4. We're going to go on to indeterminate powers with one huge example. Okay, this is all one example, right? And then I'm going to do one more part for indeterminate differences. And at that point, that'll be the end of class or lecture. And then I'm going to probably go through 9.6 or 7 or 5, I think, next, if I can. But definitely for Wednesday, by Wednesday, you should have everything done for L'Hopital's rule. There's a lot more to L'Hopital's rule than I anticipated, so my apologies. But hopefully it's very helpful. All right, guys, you guys take care. I'm going to switch off now and then go on to the next part after this. Okay, thank you guys so much. You guys have a wonderful day. Or, yeah. I'll see you in a second.